Hello, and welcome back to QED and QCD, in fact, the last lecture in this series. So last time, we looked at multiplicative renormalization and saw how that can be used to organize the divergences that one experiences at loop level. We discussed first, or we will now discuss its use for ultraviolet renormalization, and that's what's called multiplicative. It's called UV renormalization. Now, it's important to realize later on that for the ultraviolet poles, one does actually need to add counter terms into the Lagrangian to make them cancel. For the infrared poles that we'll discuss later, they actually cancel already within the theory. We just need to be able to organize them, and it will turn out that dimensional regularization will be useful for that too. So what did we do with dimensional regularization? Well, we saw that the ultraviolet problems of integrating the loop integrals would go away if we changed the dimension of space-time from 4 dimensions to something that was 4 minus 2 epsilon. Now, of course, we need to integrate our Lagrangian over space-time in order to calculate the transition amplitudes. And we remember that the Lagrangian contains terms such as a psi bar d slash minus m psi from the Dirac equation with the fermions coupled to a vector field. Now, since in 4 dimensions, this term will integrate to something that has no units, so we can exponentiate it. That means that the mass dimensions of the psi bar psi have to be equal to 3, right? Because we've got something that we integrate over x that removes 4 mass dimensions. There's 1 that's already taken here. The whole third term has to have 4 mass dimensions. That means that psi bar psi needs 3. And that of course means that the field, the fermion fields itself, have mass dimension 3/2. Now, this term here couples the psi bar with an a mu and a psi. So there's a term, the interaction between the gluons and the fermions as g psi bar gamma mu psi a mu. Now again, this whole thing, when we just integrate over d4x, has to have no dimension after integral. So that means that the vector field has dimension 1. We already know that these have dimension 3/2. So the dimension for the coupling is 0. When we just integrate over, have a theory that's well defined in 4 dimensions. Now, when we now want to change the dimension that we integrate over in space-time to 4 minus 2 epsilon, then suddenly the integral of this term no longer comes out massless. We need to rectify that. We don't want to change the dimensions of the fields. The easy way of doing this, of changing the whole term, then is to introduce a mass in the coupling, such that g, when we change the dimension of space-time, goes to mu minus 2 epsilon. That would then ensure that this whole term stays with 0 mass dimension once integrated over space-time. Now this mu is arbitrary completely. It's not fixed by the theory. essentially it's just used in order to ensure that we can organise the loop integral and multiplicative renormalisation. So we can organise the loop integrals to give finite results by using multiplicative renormalisation. Now let's see what this introduction of a mass scale in the coupling leads to. So last time we discussed how multiplicative renormalisation means that, to start with, that all the terms that we have considered in the Lagrangian are what's called the bare terms. And we just say that the bare term in the Lagrangian, which is infinite when we start calculating loop corrections, is actually some renormalization factor times the physical field that is then finite. In the same way, the gluon fields will be some renormalization factor a mu bare. So obviously, if the left-hand side, if the bare quantities are infinite, so is Z, right? So that they will have poles in epsilon in the small amount that we change space-time from 4 dimensions. Now, if we now calculate a scattering amplitude, so let's say that we have a scattering amplitude with some fermion legs and some gluon legs. So there will be NF fermion legs and some Na legs for the gluons. Now, this then means that the bare Green's function here will have a property of a renormalization, multiplicative renormalization, that says that ZA to power Na and ZQ for the fermion fields to power NF times the bare Green's function as a function of the gluon momentum and the quark momenti and the coupling will be equal to the physical scattering amplitude of the physical Green's function that is finite. That will of course also depend on Na and F, all the gluon momenta, quark momenta and coupling. Now, since the bare quantity here is mu independent, this thing here is mu independent, the sets have all the mu dependence, and so does the physical observable, well, the physical Green's function over here. So if we apply a derivative to the right hand side, we get the mu d d mu on the renormalized Green's function. We just write out what d d mu is. That's mu the partial derivative, meaning the explicit dependence, plus mu, then the dependence on mu through g. And so forth. So if we write it like this on the renormalized Green's function, not the bare one, but the renormalized one, then this is the result. Now, it is very easy, of course, to take the derivative of the powers set to the Na, because that, if we just note that set a Na just is equal to e to the Na, the log of set A, then we get that mu dd mu plus beta, beta g dd g minus na gamma a of g nf gamma f of g plus, just keep like this, of the Green's function is equal to 0, because that the bare one doesn't have any mu dependence. Here, beta of g is just a shorthand notation for mu times the derivative of the coupling with respect to mu. And gamma a of g is mu dd mu of the multiplicative renormalization factors. Now, let's analyze what this imposes with respect to the scaling properties of the Green's functions. So the Green's function is just the scattering amplitude. So what do we learn about the scaling properties of the Green's function? So if d is the mass dimension of the Green's function, so the mass dimension is the dimension in terms of masses of the Green's function, of the scattering amplitude. So if that's denoted by d, then if we take the Green's function with Na and Nf and scale all the momenta with a constant t, so everything that depends on a mass is scaled by a constant t, then the scaling properties, because of the mass dimension, is such that this will become t d gamma Na Nf and then the unscaled momenta. Like so. Now, this means that the Green's functions satisfy a relation which is that t ddt, just take the t derivative of gamma Na Nf of these. Yeah, what I have here, G tu mu tu is equal to d, take that d down, the t is already here, and then gamma Na Nf, and then I have back what I had before, which is t gi t qi g like so. Now, expanding now the derivative, writing that in terms of the partial derivatives, we find that t partial derivative with t plus mu partial derivative with mu minus d, the mass dimension of the Green's function, on gamma in A in F t with all this momentum scaled except the mu is equal to 0. Now, if we now use the equation we have up here, this one here, to eliminate the derivative with respect to mu, then we find a relation that says that minus t d dt plus beta of g d dg minus a gamma of a g minus f gamma f of g minus d, acting on the renormalized Green's function in a in f t qi g mu is equal to 0. Now that's a first order partial differential equation with some characteristic equations that are used for solving it. That says that t gg dt is equal to beta g of t. So the coupling as a function of t, the derivative of that with respect to t will be equal to beta. Now there are other characteristic equations that says here that g bar of t equals 1 is equal to some number g that we fixed, that is, a boundary condition. Now, and then one can then find an explicit solution for the Green's function, but we'll stop here by just starting to see that actually, because we have to do UV regularization and introduce bare quantities and multiplicative renormalization, that forces the coupling to depend on T. So a prediction of the uncomfortable ultraviolet feature of loop corrections is that the coupling will depend on the energy. Now that's true as well for QED, but the coupling in QCD has a different dependence than that of QED. So normally we've seen that actually for scattering cross sections it's never just 1 power of G that enters, they're always 2, 4, 6 and so on. So therefore usually the coupling structure of scattering cross sections is studied in terms of a parameter that's called alpha s, which is g squared, it's called gs squared, over 4 pi. Now the beta function for alpha s is the same, more or less, as that of g, of course, because that we see here that the coupling times t, dg dt is equal to a half t g squared dt, which is 2 pi d alpha s d ln t, which is 2 pi times what's called the beta function of alpha s. So while the Green's function here renormalized, or rather the bare Green's function doesn't depend on mu, the physical Green's function here will depend on mu because that it can only be calculated perturbatively. If one were to calculate to all orders, then one would get 0, but because one only calculates perturbatively, that's hard enough, because one only calculates perturbatively, there is a leftover mu dependence from the truncation of that series. So the cancellation of mu, and generally all renormalization scheme dependence in the theory, happens between different orders in the perturbative series. So when we terminate the series at a certain order, we introduce some renormalization scheme dependence to the theory. And so the beta function here as well can only be calculated perturbatively. And that means, of course, that we can find the coefficient in a perturbative series. So if we write here d alpha s d log q squared as minus beta naught alpha s squared minus beta 1 alpha s cubed minus beta 2 alpha s 4 minus beta 3 alpha s 5. So there are certain things that is worth looking at here. The first one is that for gauge theories, the beta function will always start at alpha s squared. There will never be a linear term in that evolution equation. Now, secondly, the first two beta function coefficients will actually be independent of the renormalization scheme. So we can write them down here as beta naught 1 over 4 pi, very famous, 11 minus 2/3 in f. This is for the number of colors equals 3, and beta 1 is equal to 1 over 16 pi squared 1 over 2 minus 38 over 3 NF. So what does it mean that the alpha s depends on q squared? Well, that means that if one, for example, calculates m squared for quark scattering, then one gets something that depends on s squared plus u squared over t squared. And that's all the energy dependence when it's summed over all spins. That's the energy dependence one gets. We note here that the mass dimension here is 0. But of course, there's an alpha s as well. And this means that if one calculates the scattering at a given energy and evaluates the matrix element squared and wants to see what happens if I scale all my energies with a factor t, then of course s is scaled with t squared, u is scaled with t squared, and t is scaled with t squared, right? Because s is, for example, pa plus pe squared. Now, you might think that therefore if you scale all momenta with number 10, then the matrix element squared would be unchanged, right? Because all S, T and U scale. But what the study here of the Green's function tells you is that actually our alpha S should be evaluated differently if we take and scale all momenta by T. Now that means that if you study, for example, a given process for a change in the T, for example, a change in the transverse momenta, then one should see that the best fit, if one uses a specific form of the scattering and says what's the best fit of the scattering cross-section for alpha S, so we measure the scattering cross-section as a function of PT, for example, in a dijet production, and one sees that as a scale of PT, one actually finds an alpha S that decreases as a best fit. And it turns out that that evolution of the alpha S as a function of PT is exactly as predicted by the QCD beta function. So the running of the coupling is a direct consequence of the need to perform multiplicative renormalization in order to get physical quantities out of our Lagrangian and prediction for cross-sections. There's a nice plot in the notes on measurements of alpha S as a function of PT, and it is remarkable how well that is described by the QCD beta function. So there are just two small topics left for us to discuss in this lecture series. The first one is infrared poles. We saw earlier that the loop intervals that we have to calculate at higher orders will indeed have poles also for soft loop momenta. So if one studies, for example, quark-quark scattering at higher orders, one will see that the loop diagrams will have poles for soft loop momenta. The question is, what do we do there? Do we have to also introduce some counter terms to regulate those? No, we do not. In fact, the infrared divergences that one sees in the theory all cancels consistently within perturbation theory. So, how does that work? Well, of course, in order to be able to calculate, we have to not just have infinity, but it turns out that if one calculates this loop interval in D minus, instead of doing 4 dimensions, we can do the same trick as we did for the ultraviolet divergences. It's just that for infrared divergences, one needs higher number of dimensions rather than fewer number of dimensions. So one needs here a negative epsilon for the infrared loop intervals to be finite. One still gets then poles in epsilon in the final expansion, or in the final expression, but one actually sees that those poles cancel within the theory. They don't just cancel within the loop intervals, but one needs to take into account the effect of soft emissions of the lex with one less loop, right? So there's a one loop diagram, and this is a let's call it Born plus 1, because there's one extra link compared to the Born amplitude. So there's an infrared cancellation between these. Now technically in QCD, there's then also a leftover divergence that is factorized into the PDFs. So that's why there's some μF dependence in the PDFs. Anyway, point is that the same dimensional treatment will let you organize the cancellation of the infrared poles and get a finite cross-section. The final bit we'll discuss is confinement and PDFs. right? So confinement, QCD confinement. What does confinement mean? Well, confinement means that essentially, because of the evolution of the alpha S, the QCD fields are confined within the hadrons. You don't see colourful quarks flying around. They're always confined in colourless hadrons. And the reason is, essentially, that starting from a meson with the two quarks bound by a strong a strong gluon field, if one wanted to pull them apart, then at some point the energy stored in the flux tube becomes so large, so one could imagine pulling them apart, in order to try and isolate a quark, but the flux tube becomes so energetic that essentially it becomes energetically favourable to produce out of the vacuum an extra quark-antiquark pair and bind them all like this, thus reducing the length of the colour flux tube. So that's why there's such a thing as confinement. A direct result of the weakening of the coupling with increasing Q squared is that for sufficiently large Q squared, if we hit a proton with a photon, for example, then the individually struck quark, so let's have a photon picture, or a proton picture here with 3 quarks in, if we hit it with a photon of sufficiently large Q squared, then the individually struck quark Q squared sufficiently large such that alpha S of Q squared is small. Another word for small here is perturbative, such that the perturbation series converges quickly. The point is that for sufficiently large Q squared, the struck quark will not have time to interact with gluons with the rest of the proton remnant. So it will not have time to interact with the proton remnant to equalize the Q, to spread out the momentum that has been hit by to the other constituents of the proton before it has left the gluon field around the remnant. Now, this means that we can actually describe the interaction between a photon and a proton as that of fundamental interactions between quarks and photons, and the probability of finding a quark within the proton, and that's what the PDF does. Now, the magic here is that not only does it work for DIS, where we strike a proton with a photon, but it also works in proton-proton interactions. So the idea of a PDF, which describes the probability of finding a quark, say, of a given momentum fraction of the proton within the proton, also works for PP interactions. So for example, PP to W. You might say, but what functions then as the probe of the proton? Well, what we have here, of course, is that the proton still consists of quarks and gluons, but the fundamental interaction that we probe is that of a, well, you can view of it as two DIS processes put together. We strike a quark in each proton with the created W. And here we can also use factorization to extract the quark from the proton and let it interact in on-shell scattering amplitudes that we can calculate, as we did earlier in this course. Even though that the state that we start from is that of confined protons. That marks the end of this course. I hope you enjoyed it. You're welcome to contact me if you have any questions, either directly to the course or anything else. Thank you very much. Bye.